Hello there, Mr. Sutton here, bringing you the BC Calculus 617 lesson on Euler's method. In this one, we are going to approximate particular solution values of differential equations using Euler's method. We'll start this lesson off with a warm-up on tangent lines. Use a tangent line from x equals 1 to approximate f of 1.3 for x to the fourth. Pause the video, give it a shot. All right, let's see how that went. So hopefully you started with the tangent line formula. L of x equals f of a plus f prime of a times x minus a, where a is your x value of tangency, 1 in this case. So applying that, we can write f of 1.3 is approximately equal to, because we're not actually giving the true value here, f of 1 plus f prime of 1 times x minus 1. At this point, it's just a matter of finding all these different values. And we could pretty quickly figure out what f of 1 is just by plugging into this formula, but we'll need the derivative to get f prime of 1. So f prime here is going to be 4x cubed. And now plugging things in, f of 1, that's going to be 1 to the fourth, plus this is going to be 4 times 1 to the third. And 1.3 minus 1, we can do that right away. That's just 0.3. So then this is just 1 plus, let's see, 4 times 0.3 is going to be 1.2. So that ends up being 2.2 when the dust settles. So we've seen that we can approximate function values with tangent lines, but the further you get from the point of tangency, the less accurate your approximation gets. Euler's method tries to fix this. Euler's method, the basic idea at least, is we're approximating function values with not one, but a series of tangent line segment approximations. So for example, let's say we have some function here, and let's say that we're starting somewhere over here, and we're trying to get the y value somewhere over there approximated. So we could start with just a single tangent line, but of course, if you're trying to approximate the y value over here, and we just follow this tangent line, like we're way down here, even off screen. So what Euler's does is it stops at some point and calculates a new tangent line trajectory based on the current y value and x value and the current slope. So we draw another tangent line, and of course this is also going to veer far away from what we actually wanted for an output, so we can stop again and calculate another tangent line. And we can keep doing this until we get to the x value that has the y value we wanted. Now you might be saying, well, this is still a little bit off. I'd like to get even more accurate. So to get a better approximation, we can just use smaller step sizes. So stop a little bit sooner before you calculate that new tangent line. But the idea is the same. We're just calculating a series of tangent line approximations to get us as close as we can to that value. So this is kind of a neat method, but where do we actually need it? So this tends to be good for finding particular solutions to non-separable differential equations. So if you have something where you can't get the y under the dy without also dragging some x's with it, or if you have a table where you don't even know the exact formula. So now that we've got the basic idea of Euler's method, let's use it on this problem, where we're trying to use it with increments of 0.1 to approximate y when x equals 1.2. So we're given x minus 1 as our starting differential equation, and initial condition of f of 1 equals 2. So you might be wondering, well, how do I know I have to use Euler's, because I could totally do this with fundamental theorem of calculus. The good news on the AP exam is that they will tell you to use Euler's when they want you to use it. The rest of the time, you generally have to use something else. So let's start by getting a strategy here. Since I'm trying to go from x equals 1 to 1.2, going by steps of 0.1, that means I have to first find f of 1.1. So our first step is to approximate f of 1.1. And then once we have a value there, we're going to use that value plus the derivative at 1.1 to approximate f of 1.2. So two approximations. Now, for those of you who like formulas, at every step of the way we're going to be using this formula. F of some starting value plus some step increase is going to equal f of a plus f prime of a times, and you might be thinking x minus a here, because this is kind of like the tangent formula, but we're just going to say delta x. So instead of going the whole distance from our starting value to the value we want to approximate, we're only going one step at a time, so it's always just consistently delta x. All right, So to get f of 1.1, we're going to start by doing f of 1, and we're writing approximately equals here because this is an approximation right away, plus f prime of 1 and delta x, which in this case is going to be 0.1 because they said 0.1. So let's fill in a few values here. F of 1, they actually gave that to us. That's going to be 2. And we also got f prime of 1, which we don't know quite yet. So let me go and calculate that off to the side here. That's just going to be what I get when I plug 1 into my differential equation. So that's 1 minus 1, which is 0. So we can write plus 0 times 0.1. And this clearly comes out to just 2. Now, you might be wondering, why am I writing equals versus approximately equals? Well, this stuff right here was an approximation of f of 1.1. This stuff down here is exactly what the stuff I just wrote equals. So the general rule of thumb with equals versus approximate is if the stuff on the right side of your sign is an approximation of the stuff on the left side, use approximately equals. If it's the exact value, then you can use a real equals. So let's keep going because we still need to get f of 1.2. So to get that, I am now going to have f of 1.1 plus f prime of 1.1 times my step size of 0.1. Now, what's f of 1.1? Well, we don't actually know, but we have an approximation for it right here. Since 2 is an approximation of f of 1.1, I'm going to now write approximately equals 2. Plus, we now need the derivative at 1.1. That's going to be 1.1 minus 1, which is 0.1. So then we're adding 0.1 times the step size, which also happens to be 0.1. So this is 2 plus 0.01, which is 2.01. And again, if you're wondering the difference, why we have an approximate versus an equals, we needed approximately 2 here because, again, f of 1.1 was approximated, whereas f of 1 up here, we knew the exact value of it. All right, the name of this next example is why, Euler, why? Because this time instead of x minus 1, we have y minus 1 in our differential equation, which is a little bit of a game changer. This time we want Euler's method with 2 steps to approximate f of 4.6, and we're starting with 4, 3. So pause the video and see how far you can get on this one. All right, so to start off, they didn't tell me the step size, but they did tell me I need to do 2 steps, and I have to get from 4 to 4.6. So that means that I have to cover 0.6 in 2 steps, so 0.3 is my step size. So starting off, I'm going to do f of 4.3, and I'll approximate that, and then I'll get f of 4.6 based off of what I figure out here. So this is going to be f of 4, which we already know, plus f prime of 4 times, we said 0.3 for the step size. And let's see, f of 4, they told us that was 3. Now for f prime of 4, we have to go ahead and plug that into our differential equation, but this takes y values, not x values. So we're going to plug in the y value 3, because that is the y value when x equals 4. So note again that we're plugging y values in. Now in terms of notation, I'm going to write f prime of 4 equals 3 minus 1. Notice that I didn't even specify the 3. It's just kind of assumed that if you're plugging in 4, you're also getting the y value that goes with 4. And I've looked this up, and this is in AP rubric, so this is definitely legit to write it like this, believe it or not. So this equals 2. So plugging that back in, we've got plus 2 times 0.3. So that's 3 plus 0.6, which is going to be 3.6. All right, one hurdle passed. Let's go on to the next one, finding f of 4.6. So this is now going to be approximately f of 4.3 plus f prime of 4.3 times 0.3. F of 4.3, again, we don't know the exact value, but we got this approximate value of 3.6. So I will write approximately equals 3.6. And now for f prime of 4.3, so this one we're actually going to have to approximate because this, remember, takes y values, and we don't have the exact y value at 4.3, so we're going to use 3.6. Since we're using an approximated y value in our derivative, this derivative itself is now going to be approximated. So this is going to be approximately 3.6 minus 1, which is 2.6. So that gets plugged back in here, 2.6 times 0.3. And if this is a free response, we could leave it like this, or we could simplify it. Let's see, if I have 3 times 26, that would be 60 plus 18, so 78. So 0.78 plus 3.6 would be 4.38. And if you're wondering, are you allowed to use a calculator on these? Believe it or not, most of the time, these are no calculator questions. So get that arithmetic by hand ready if you need it. So on the first two examples, we could have actually found the exact value of both of those using just normal diffie-q math. We would have gotten it wrong because they specified Euler's method, and if you don't use that, you get a different number. This problem, there's no choice other than to use Euler's method. We don't know what the derivative actually looks like other than these selected values of it that they've given us in this table. So given this table, if f of 2 is 4, we want the approximation to f of 1 using Euler's with 2 steps. Pause the video and see where you can get on this one. All right, so this is a little bit different than the other problems in another way other than the table format. We're going from the x value 2 to the x value 1. So if you're going backwards, you need to use a negative delta x. So our next step is going to be to do f of 1.5. We have to go by 0.5s backwards. So this is going to be f of 2. We're starting at 2 and going backwards, plus f prime of 2 times a step this time of negative 0.5. So f of 2, they gave us, that was 4. The derivative at 2, f prime of 2, that's right in the table here, that's 0.9. And then again, negative 0.5 for our step. So 9 times negative 0.5, that's going to be negative 0.45. 4 minus 0.45 is going to be 3.55. And we continue. So we already got f of 1.5. Now we need f of 1, which is our ultimate goal here. So that's going to be approximately f of 1.5 plus f prime of 1.5 times, again, our step of negative 0.5. And this time around, we use the approximate value of f of 1.5. That's 3.55. F prime of 1.5 up here is 0.5, and we have a step of negative 0.5. So this is 3.55 plus negative 0.25, which comes out to 3.3. So that's it. Hope you enjoyed Euler's method. Till next time, Mr. Sutton signing off.